Just like solid objects can exert forces on each other, fluids also exert force on any object in them. This is why some things float while others sink, and why temperature changes with elevation. We've said that density allows you to predict whether an object will float or sink. It can do this because the forces that affect floating and sinking in fluids depend on the two properties that make up density, namely mass and volume. The two main forces acting on an object floating in water are gravity and buoyant force. Gravity, or the object's weight, pushes it down. The strength of gravity depends on the mass of the object, so the more mass an object has, the stronger the sinking force will be. Buoyant force pushes up and depends on volume, so the force that can make an object float depends on the volume of the object. If volume and its force, buoyant force, is higher than the mass and its force, gravity, then the net force points up and the object will float. Since these forces depend on mass and volume, whether an object floats or not depends on density. We haven't said why buoyant force pushes up or why it depends on the volume of the object yet. This force exists because when an object goes into a fluid being pulled down by the force of gravity, it collides with and displaces some of that fluid's particles. When you drop ice cubes into a glass of water, the water rises because the ice has pushed some of the water particles away. Newton's third law works even on individual particles though, so when these particles are pushed and displaced by the submerged object, they push back. The submerged object pushes down on them, so they push it back up. The more particles the submerged object displaces, the stronger the net upward force is going to be. The larger the volume of the submerged object, the more particles it will displace, so the larger the volume of the submerged object, the stronger the upward force will be. This force, again, is called buoyant force. Archimedes' principle tells us exactly how strong buoyant force will be. It says that the buoyant force acting on an object is equal to the weight of the fluid displaced by the object, but acts in an upward direction. If dropping a rock into water causes 3 pounds of water to displace, then the water will push back up on the rock with a buoyant force of 3 pounds. If the rock weighed 7 pounds out of the water, it would only weigh 4 pounds in the water, because of the buoyant force pushing up against gravity. The buoyant force pushing up cancels out some of the force of gravity, so its net downward force is only 4. If an object is less dense than water, the water it displaces will weigh more than it does, so buoyant force will be stronger than gravity, and the object will float. Since fluids are composed of active molecules, at least compared to solids, they are constantly moving, pushing upwards and applying force to molecules or whole objects around them. The air around you is always pressing down on you in all directions. If you put air into a balloon, it becomes firm because the air is pushing out in all directions. If you go deep underwater, your ears hurt because they are sensitive to the force pressed in on them by the water. Since we're dealing with a lot of small objects and forces rather than a single object and force, and since these forces act equally across the entire surface of whatever object they're encountering, it's easier to look at how much force is exerted on a small unit of area, such as 1 square meter or 1 square inch. The amount of force exerted over a unit of area is called pressure. Whole objects exert pressure, not just fluids, which is why a needle can easily puncture your skin while the eraser on a pencil can't. But it is especially useful when dealing with fluids. If you press down on the desk with the palm of your hand, and then the tip of one finger, you'll find that it strains the tip of your finger more than the palm of your hand. This is because you're concentrating the force and increasing the pressure. A lot of force on a small area means high pressure. Since fluid molecules have a lot of energy, the smaller space you squeeze them into, the more pressure they will exert. If you put too much air into a balloon, it pops, because the pressure is too high for the rubber to sustain itself. Our atmosphere is a giant mixture of gases, a fluid, so it exerts pressure on everything in and around it. An air molecule at a low elevation has a lot of air molecules above it, and their weight is pressing down on it. This means that it is being squeezed into a smaller space and pushed closer to the molecules around it, which then means that it will exert more pressure on the objects around it than the molecules at higher elevations not under so much pressure. This kind of pressure exerted by the air on objects is called atmospheric pressure. As you increase in elevation, this atmospheric pressure decreases. As atmospheric pressure decreases, the particles have more space, collide less, and, as a result, don't carry as much energy. This means that temperature also decreases as elevation increases. The opposite happens when you go to lower elevations. Water is also a fluid. It also exerts pressure on any objects in it. Just like air, the deeper you go, the more pressure you feel. By the time you reach a depth of 10 meters, approximately 33 feet, the amount of pressure on your body is the same as if our sky were twice as thick. Every 10 meters down underwater is the equivalent of adding an entire new atmosphere. Our bodies are adapted to the amounts of pressure present at sea level. If we go up into the air or below water, our bodies have to acclimatize. However, the range that our bodies can acclimatize is relatively small, so diving really deep or flying too high can be dangerous. To account for this, airplanes are pressurized to keep the pressure from dropping too low during a flight, and people exploring the bottom of the ocean have to use submarines or robots instead of scuba gear to avoid being crushed. Our bodies are filled with fluids, especially the air in our lungs, so when we change elevations, the pressure in those parts of our bodies also change, and they don't work properly. This is why it's hard to breathe at the top of a mountain, and also why your ears pop when you fly. We can change the amount of pressure a fluid exerts by changing its speed. By changing the speed of the fluid flowing over or under an object, you can use the pressure to pull or push that object up and down. Bernoulli's principle says the pressure in fluid decreases as the fluid's velocity increases. So the faster the air or water goes, the less pressure it exerts, and the slower it goes, the more pressure it exerts. If you slow down the air under an object, the particles spend more time in contact and exert more pressure, pushing the object up. If you speed up the air above the object, it will decrease the pressure and pull it up. The rudder of a boat slows down the water on one side, which pushes the back of the boat to the other side and turns the boat. Birds have been using this principle as well for millions of years to fly. Humans took inspiration from the birds when they started building airplanes. The engines of the plane push it forwards, and the shape of the wings causes the air moving over them to go faster than the air going below them. The difference in pressure creates an upward force called lift, which allows the plane to fly. Another interesting aspect of forces in fluids is described by Pascal's principle, which says that a change in pressure in an enclosed fluid is evenly transmitted throughout the fluid. This means that if you exert a small force on a small area of an enclosed fluid, it could result in a large force being exerted by the fluid on another part with a larger surface area. This is what allows hydraulic machines to lift incredible weights. Anyone who has ever seen a car lifted up in an auto garage has already seen it in action.